All right, so welcome back. So in the previous lesson, we had a look at how to analyze equations and graphs of polynomial functions involving the factored form of a polynomial function, where the zeros are, how do we determine when it's going to be positive or negative within the entire interval. Um, and we also had a look at how to write equations based on the polynomial function that is given. So in today's lesson, we're going to have a talk about transformations of power functions, and then later on, we'll talk a little bit about the transformations of polynomial functions. All right. So recall that in previous years that we had a look at transformations of different types of functions, including the quadratic function, the absolute value function, the radical function, the reciprocal functions, the exponential functions, and many more. So the goal in this lesson is to be able to transform any power functions and as well at the end polynomial functions. So recall that in general, if y is equal to f of x as a function, then the transform function g of x is defined as follows. So whenever we want to transform a function, we got to keep the function in hand, but we also have to adjust the parameters as well. So that is, so we want to write a function of g so that we have, so g of x is going to equal to a times f of k times x minus d plus c. Now you might be wondering what are these four parameters, namely the a, the k, the d, and the c. Well, let's write down the following descriptions of these parameters and what do they do. So for a, usually a represents a vertical stretch or compression. Vertical stretch or compression. And then k here represents the horizontal stretch and compression. And then D and C both represent the um, horizontal and vertical translations, respectively. So horizontal translations. And vertical translations. So we usually call f of x the base function of the family of functions, which is basically the simplest form of a function that we can use. So let's have a look at each of the parameters and see what would they do. So let's have a look at the vertical stretches and compressions first. So let's say we have a power function of the form f of x is equal to x to the n, where n is a whole number, positive integer. Then if we transform the function to g of x with the given parameter a, so we would say that g of x is ax to the n, then there are three possible cases. So for case one, let's say if a is greater than 1, then we say that g of x has a vertical stretch by a factor of a. So basically, when we see quadratic functions, usually we would have sort of this shape as like a base function of our quadratic function. Then if a was like greater than 1, for example, it would start to get a little bit more close and condensed into inside. But we would notice that all the y coordinates are going to be multiplied by 2 each time. But we'll have a look at that, see how it works. So next one is like if what happens when a is not 1, but actually it's going to be between 0 and 1. So let's say if the absolute value of a is between 0 and 1. So it could be a negative, it could also be a positive a, but the main focus here is that we're focusing on the absolute value of a. So then g of x has a horizontal, not horizontal, vertical compression by a factor of a. So basically the same story, but basically we're going to have the function, basically the y coordinates are going to be stretched out. So it's going to be less than what we would with the base function. And then the last function, last condition is when a is just below 0. So if a is less than 0, then g of x has a reflection about the x-axis. So meaning that every y coordinate of the base function is going to be flipped to the negative side. So it's going to go to the negative y coordinate. So if we say we have something like this shape, for example, some function, then every coordinate is going to be transformed mirrored to this point down here. And same thing with this one is going to come down here. And this is going to be somewhat like your new function. Something like that. All right, so with all these three conditions, let's see what happens, what a graph would look like if we had a look at all three cases. So for this example, let's use the base function y is equal to x squared. So we're having a look at the parabola in this case. So let's sketch the parabola. So I'm gonna go by one unit per two boxes. So this is 1, this is 2, here is -1, here is -2. And then on the y-axis, I'm gonna go by ones as well per every tick. So that's gonna be 1, 2, 3, 4. And I'm also gonna go -1, -2, -3, -4. All right, so let's label the points of the quadratic function. These points should be pretty common right now. So usually when x is equal to 1, y is equal to 1. When x is equal to 2, y is equal to 4. And same thing on the other side. And we would have here as well. So we have this quadratic function. Let's try to sketch this. And we have the other side as well. So we have this quadratic function. This is our base function. So let's have a look at the first case. So the first case says that when a is greater than 1, then g of x has the vertical stretch by a factor of a. So let's just say that for the first case, we use some function like, let's use y is equal to 2x squared. So here we would know that a is equal to 2 this time. So what this would look like is that every every y point that we have at our base function is going to be multiplied by this 2 over here to get the transform function. So that means, for example, at x is equal to 1, we would have the point, so y is equal to 2 times 1 squared, which is equal to 2. So everything is just going to be doubled at this point. So we would still have the 0 point at the origin. And then 1, when x is equal to 1, we said that it's going to equal to 2 now. So everything is going to be stretched vertically. And same thing on the other side, we'll have something like this. And now the 4 here is just going to go beyond, so we'll just try our best to approximate it. But this is what the function would look like now. We have this. Yeah. So this is the second the first case where we have a vertical stretch greater than 1. Okay, so for the second case now, we will have a look at what happens when g of x is between, or a, the absolute value of a, is between 0 and 1. So this means that g of x is going to have a vertical compression. So every y coordinate now is just going to be reduced to half of it. So let's use the function. Y is equal to half x squared this time. So for example, at x is equal to 1, then y here is going to be half times 1 squared, which is equal to 1/2. So when x is equal to 1, y is going to equal to 1/2. So this is what the function would look like. So we would still have the 0 point here at the origin. And then at x is equal to 1, it's going to be a half. And then at x equals -1 is also going to be -1/2. Then when x is equal to 2, it's going to go to 2. And then -2 would also be 2. So we would see that in order to get from this point, the base graph, to this point here, everything has to be divided by or reduced to a half. So for example, the one at y equals to 1, it's going to be transformed to half its value. And same thing, for example, at 4, it's going to be reduced to half its value, so it's going to be at 2. So this is what the function is going to look like then. So it's going to be stretched by a factor of 1/2, like this. So this is what happens when 0 is between the absolute value of a. The absolute value of a is between 0 and 1. And then for the last case, we're going to have a look at what happens when we look at case 3 now. So when a is less than 0, then g of x has a reflection about the x-axis. So let's just say, do something simple. So let's just say we have y is equal to -x squared. So for example, at x is equal to 1, we would have then y is equal to -1 squared, which is equal to 1. -1. So everything that we have here is going to be reflected down to here. So for example, this point is going to go all the way here. This point is also going to go all the way here. This point at 4 is going to go all the way to -4. This point is also going to go to -4, and so on. You'll see. So this is the third graph. So we have the points. So every point in the base function is going to be transformed to reflect, so that it's going to be reflected over the x-axis. So we would have this point and this point. So this is what the function would look like. There we go. So this is what happens when a is less than 0. Okay, so those are the 4 graphs that we have observed. So this red line over here is just going to be the base function of x squared. The blue graph basically shows what happens when we have a vertical stretch. So every y value is simply just going to get larger at each point. And then the green line shows that all the y values are going to be compressed. So it's going to go closer to the x-axis than the base function. So I just said. One way to remember whether it's going to be a stretch or a compression is simply as follows. So for vertical, so first one is a stretch, right? It is going to go away from the x-axis. So every point is going away from the x-axis. And then if it's a compression, then every point is going towards the x-axis. So that's two ways where you could remember whether it's going to be a vertical stretch or a compression. Okay, so that's the vertical stretches and compressions. Now let's have a look at what happens when you have a horizontal stretch and compressions into the transformations. So suppose we're given the power function like usual, f of x is equal to x to the n. Then if we transform g of x to g of x with the parameter k, where k is going to be the parameter that represents the horizontal stretches and compressions, and same thing, we're going to have three possible cases as well. So now let's just say what happens when k is greater than 1. So if k is greater than 1, then g of x is going to have a horizontal compression. Now this time it's going to be a little bit different because now it's going to be dealing with compressions, and it's always going to be 1 over the value of k that you're going to work with. So by horizontal compression by a factor of 1 over k. So that's always going to be the case with horizontal stretches and compressions. You're always going to take the 1 over the value, because if we kept it as the k value, it's going to be representing the vertical, right? But if we take it 1 over, we're flipping it, we're going to be having a look at the what happens to it horizontally now, not vertically. So similarly, when the absolute value of k is between 0 and 1, then g of x is going to have a horizontal stretch. To have a horizontal stretch by a factor of 1 over k. All right, so that's the second case. Basically the same thing. It's going to be going closer towards the y-axis this time for the second case. The first case is going to go away from the y-axis this time. Okay, so the last case, when k is less than 0. So if k is less than 0, so with vertical stretches and compressions, we know that when a is less than 0, then we're going to have a reflection over the x-axis. But when k is less than 0, we're going to have a reflection over the y-axis this time. So then g of x is going to have a reflection about the y-axis. So these are the three scenarios that we have. So when k is greater than 1, we're going to have a horizontal compression. And then when k is between 0 and 1, the absolute value, I mean, then it's going to have a horizontal stretch. And then last one, when k is less than 0, it's going to have a reflection about the y-axis. All right, so same thing. Let's have a look at the three graphs that we're going to look at. This time, our base function that we're going to select is going to be the cubic function. Keep it simple. All right, so the cubic function usually goes like this. So I'm going to go same numbers here. So we're still going to have a 1, 2. But this time on the y-axis, I'm going to go up by 2's each tick. So 2, 4, 6, 8. And then same thing the other side, we're going to have -1, -2. And then this side we have -2, -4, -6, -8. All right, so we have the cubic function at the points. So we're going to have 1, 1, and then 2, 8. And then we have -1, 1, -1, -1, and -2, -8. So let's connect the graphs. Connect the points. There we go. So that's our base function. Y is equal to x cubed. So let's do the same thing. Let's have a look at the first case. So whenever we have a horizontal compression or compression by a factor of 1 over k, this k over here is going to go inside the function. So let's just say we're going to have the horizontal compression of a factor 2, 1 over 2. So that means inside the brackets, we're going to have 2x to the third. So notice that, okay, we're going to still say it's a 2 over here, but what we actually mean is that it's going to be a horizontal compression by a factor of 1 over k. Or if you could see this clearly enough, you could also rewrite this though. You could also say that we could write g of x, you have 8x cubed, because 2 to the power 3, if we use our exponent rules, we would get 8x cubed, which is exactly the same as a vertical stretch by a factor of 8. So this is sort of like a trick that you could use to remember. A vertical stretch is pretty similar to a horizontal compression. And similarly, a vertical compression is similar to a horizontal stretch. All right, so this is what the function g of x would look like here. So for example, at x is equal to 1, let's say, so i.e. g of 1, we're going to get 2 times 1 cubed, which is just going to be, so we have 2 times 1 cubed, which is just going to be 2 cubed, which is equal to 8. So that means that g of 1, we're going to get 8. And basically, if we find the other points as well, we'll have at 0, and then we'll have at -1, -8. So we have something like this. So we would see that, okay, it's also looking like a horizontal stretch, which I just mentioned. But we would notice that from the base function, all the x values are going to go by a half. So it's going to get reduced to a half. So it's going to go closer to the y-axis whenever it's a compression. So this is when k is greater than 1. All right, so similarly, let's have a look at what happens when we have a horizontal stretch. So for example, let's take the function g of x is equal to 1/2 x close bracket cubed. So basically now we have a horizontal stretch by a factor of 2 this time. So if we take the 1/2, this is also the same as saying 2. So we could also rewrite this equation a little if we choose to. So we could say that g of x, we could also do this times x cubed. So we're just expanding the powers a little. And after we expand them a little, we would get 1/8 times x to the power 3. So it looks like that we're going to have a vertical compression by a factor of 1/8, but we're going to have a look at this as a horizontal stretch. So let's have a look. So at g, for example, g at 1, or actually let's use g of 2 instead. So when g is equal to 2, we're going to get 1/8, or actually let me do it this way, 1/2 times 2 to the power 3. So we would see that this 2 cancel. We're just going to get 1 to the power 3. And that is equal to 1. So that means g of 2 is going to be 2 now. Or 1, I mean. So g of 2 is going to be 1. So every y value, or every x value now, is going to get doubled. So for example, this point is at 2. So that means we would expect it to go to 4 next, which is actually true. So if we continue the ticks a little on the x-axis to go to 4, we would see that at this point as well. So we have 2. It's going to double 2 times. So it's going to go all the way to 4, this point here. So we have a point at 4/8. And then we would also have a point at 0/0 still. And then -2, -1. And then -4, -8. So let's connect the graph, and this is what we get. So that's what we have. So that is what happens when we have the absolute value of k between 0 and 1. And for the last graph that we're going to have a look at, let's just say that see what happens when we have a reflection about the y-axis this time. So that means let's take the function g of x to be negative x to the power 3. So it will look something like this. So whenever we have, so we're going to take every point in the base function, and we're going to flip them over to the other side of the y-axis. So for example, if we take 1, 1 here over, it's going to go all the way to -1, 1. So we're flipping every single point to go from 1, 1, and then this point would go over here. Same thing, if we take -1, -1, that's going to go all the way to 1, -1. And same thing for the other points, to -8 and -2/8 this time. So this is what the reflection would look like now. And there we go. So that's the horizontal stretches and compressions. So the third case that we had to look at is what happens when k is less than 0. So all three cases, basically they're going to be similar to the vertical stretches and compressions, but there's some slight modifications sometimes that you're going to have to deal with in other functions as well. But with polynomial functions and power functions, they're going to be a little bit different. All right. So we had a look at the two stretches and compressions along with the reflections. Now let's have a look at the other two parameters, which are going to be the translations. So the first thing that we'll have a look at is the horizontal translations. So once again, we have a base function of f of x is equal to x to the n. And if we want to transform it to g of x with the parameter d given by x minus d to the power n, so what we did here is simply take the base function and we put everything with x minus d here. And I should also clarify for this g of x here, we simply took g of x and put f of k of x inside of it. And same thing for this one, g of x is equal to ax to the n. This one, we just simply put g of x is equal to a times f of x. All right, so that should clarify it a little. Then with the horizontal translations, there's just two possibilities or two cases. So let's say if d is greater than 0, meaning that, so we would have something of the form g of x is equal to x minus d to the n. Then we're going to translate to the right. Then g of x is translated horizontally. Horizontally translated d units to the right. So that should be pretty simple to understand. So when d gets larger, it's going to go more to the right. But when the absolute value, or when d is less than 0, let's say now, then we would assume that it's going to be the opposite. So it would look something like this. You'll have a g of x, and then you have the x plus d this time to the power n. So just to be careful, whenever you see plus sign, that means it's going to be the case that d is less than 0. But when d is greater than 0, you would see that you would have the negative sign instead. So you've got to be a little bit careful. It's just a little bit trick. All right, so then g of x is horizontally translated d units to the left. So just those two cases, not too bad. Which we already had to look at something similar to this with quadratic functions. So let's once again do a little visualization of these two cases. So let's say we take the base function of y is equal to x squared. So we'll have a look at the parabola again. So once again, I'm gonna use the same parameters as I did last time. So we have 1, and then -1, -2. I'll go all the way. So 3, 4, -3, and -4. Don't need to worry about the below the axis just yet for this case. So we have the parabola similarly as the vertical stretches and compressions. And we have something that looks like this. All right, so let's just say for the first case, we want to move it to the right. So let's just say we take the function g of x, for example, to be x minus 1 squared. So that means we're going to be shifting each point 1 unit to the right. So that means 1 unit to the right. So a quick visual would look something like this. So let's say we take this point over here. We're gonna move it 1 unit, so it's gonna come over here. Same thing, if we take this point over here, we're gonna move it to the y-axis. Take this point, move it to 1. Take this point, we move it to 2. And then last one, we take this point, we move it to 3. So we just connect the blue lines now, and it will look something like this. So that's just what happens when d is greater than 0. One thing I forgot to correct is the absolute values around this d. So d less than 0, it wouldn't make sense if we said -5 to the left, right? So that's why we put the absolute brackets around it. Okay, so now let's have a look at what happens when d is less than 0. So let's just say we have g of x still. Now let's just say we move it 1 unit to the left. So the blue graph represents when d is greater than 0. The green graph that I'm going to do is going to be when d is less than 0. Okay, so that means if we take the base function, we're going to move it 1 unit to the left. So it's going to go from -2 to -3, -1 to -2, from 0 all the way to -1. And then we have here, and same thing. So this point will come over here. Yeah, so now we just connect the green lines, green dots together. And it will look something like this. So the green line represents what happens when d is less than 0. So that means we're going to go 1 unit to the left. So those are just the two cases, nothing much about this one. Now for the last case, last parameter, we're going to have a look at the vertical translations. Now with same thing with the horizontal translations, we only have 2 possible cases. So for the first case, let's just see what happens when c is greater than 0. So when c is greater than 0, so that means we're going to have like plus here, this plus sign. So that means we're going to be going upwards. So every y value that we have for f of x, if we add c to it, it's just going to go up. Every point of f of x is just going to go up by 1. So that means g of x has a vertical translation c units up. Now similarly, when c is less than 0, g of x has a vertical translation c units down. So it's just either going to go up or go down. Nothing. So let's have a look at the visualization. This time we'll go with the base function using the cubic one. So base, we'll have a look at y is equal to x to the 3rd power, make it simple again. So we're going to use the same axis. So we're going to go up by 2's this time. 6, here we have 8, -4, -6, and -8, and then we'll have -1, -2. All right, and then we have the points. And then we have the points down here. And then we just connect the dots together. Okay, so that's our cubic function, the base function for cubic. Now let's see what happens when c is greater than 0. So let's just say we take the function. So we have x cubed as our base function. And then let's say what happens when we add 1. So that means we're going to go 1 unit up. So all the y coordinates that we have in the base function is going to get increased by 1. So for example, take the origin point, for example. You go up by 1 unit, so it's going to come over here. We take 1, 1, it's going to go to 1, 2. Take 2, 8, this is going to go to 2, 9. And similarly, negative 1, 1, or negative 1 is going to go to negative 1, 0. And this point is going to come here. So this is what the function would look like then. So that is what happens when c is greater than 0. And then similarly, let's say we take this c less than 0. So we'll have x cubed minus 1, let's say. So that means we're going to go 1 unit down. So forgot to put the absolute brackets around. All right, so that means if we're going to go down from the base function, we're just going to go down 1 instead. So take this point, go 1 unit down, and so on. This point is coming here, and this point comes here. So this is what the function in green would look like then. Like that. So that's when c is less than 0. So we had to look at the 4 parameters already. We had to look at the vertical stretches and compressions first, where we note that when a is greater than 1, then we have a vertical stretch. When the absolute value of a is between 0 and 1, then g of x has a vertical compression. And then when a is less than 0, it's just a reflection about the x-axis. So those are the 3 cases for the vertical stretches and compressions. Then we had to look at horizontal stretches and compressions. So when k is greater than 1, we'll have a horizontal compression. When the absolute value of k is between 0 and 1, then we're going to have a horizontal stretch. And when k is less than 0, we're going to have a reflection about the y-axis. One thing I should put instead is the absolute value of k and the absolute value of a as well. Because basically, if we have -3, let's say, it's still going to be a vertical stretch, but it's just going to be reflected over the x-axis. So we just put the absolute brackets around. And then we had to look at the horizontal translations, where we note that when d is greater than 0, then g of x is horizontally translated d units to the right. And when d is less than 0, then g of x is going to be horizontally translated d units to the left. Okay, so with these two, and then the last thing that we had to look at was the vertical translations. So where we note that when c is greater than 0, then it's a vertical translation, c units up, and then c less than 0, vertical translation, absolute value of c units down. Okay, so those are the 4 parameters. We explored them all. Now let's just say that see what happens when we try to combine all these transformations. So now that we had a look at all the effects of each parameter, let's see what happens when we combine the transformations together. So if we have f of x as a power function and we transform the power function to g of x using all 4 parameters, then we're going to have g of x to be, so we're going to have a factor of a, and then we have the power of k inside. Oops, yeah, k, and then you have x minus d being the horizontal translation. And then we have to the power of n and then plus c. This is because, okay, if we consider g of x, remember that g of x, if we consider any transformation, this is going to be f times k x minus d and then plus c. So basically, whatever we had out here, which is the function, is going to come out here. So the parameters a, k, d, and c are all the same as above. So in order to graph transformations of functions using all four parameters, we must apply RST in this order, which means, so the R here means reflections always come first. And then S would represent the stretches and compressions. And then T would just represent the translations. So this is basically the algorithm that we would follow whenever we want to graph transformations of power functions, or basically any functions at all. We use the RST method to graph them. So let's have a look at an example. Or first, let's have a look at a quick remark. So we've seen transformations like this in previous years whenever we had a look at the vertex form of the quadratic function, which was given by this function. So we have g of x to be a, and then x minus h squared plus k, where h and k is the vertex of the parabola. But if we have a look at the power functions carefully, using our exponent rules, or basically what we have a look at right now, g of x can also be written as something similar. So if we say that g of x is going to be x minus d to the n plus k, we sort of have like this center point, or like the vertex, for example, which is basically the general case for a power function. Okay, so the second remark that we'll have a look at is basically using some exponent rules. We could simplify this g expression up here to make it a little bit more simple to look at, but that's something optional that you could do. But let's just say, so we have g of x is equal to a times k to the n, x minus d to the n plus c. So what I'm going to do is going to expand the powers, bring them inside each, so that we have a k to the power of n times x minus d to the n plus c. Now that looks similar to what the vertex form would look like, where if we just join these two parameters together, we would get the exact same form as what we would have if we had a vertex form of a parabola, or technically the vertex form of a power function. All right, so now let's have a look at an example. So let's say we have the function f of x is equal to x cubed, be the base function of the cubic function. So let's transform the function from f to g with the following conditions. So the first condition is that we have a reflection in the x-axis. We have a vertical stretch by a factor of 2. We have a horizontal stretch by a factor of 3, and horizontally translated 1 unit to the right. So let's write the equation of the transform function and graph the function using RST. So let's write the function first. So we have the base function given by f of x is equal to x cubed. And we want to transform it so that we have something that reflects the transform. So we have x minus d plus c, or g of x here then would be a times k times x minus d to the power n plus c. So here we have the following conditions. So we could join 1 and 2 together. So you have a reflection in the x-axis and a vertical stretch by a factor of 2. So that these 2 points correspond to the a value, which is going to be less than 0. But it's going to have a vertical stretch by a factor of 2. So that means g of a here would be -2. Now that we also have a horizontal stretch by a factor of 3, that means k, remember that it also has to be 1 over k. So that means we're going to have the value 1 over 3 inside the k. And d for the horizontal translation, 1 unit to the right. So that means d is equal to 1. And since there's no vertical translations, we just put c is equal to 0. So that means our transform function is going to be the following. So we have g of x is equal to -2 times 1 over 3 x minus 1 to the power of 3 plus 0. Or we don't have to include the 0 if we don't want to. So that's the function that we wish to graph. So let's start using the RST method. Okay. So let's draw the base function first. So I'm going to use the same parameters as what we did. So 2, 4, 4, 6, 8, and then 1, 2, -1, -2, -2, -4, -6, and -8. Okay. First, we'll sketch the base function. So we have the origin point. We have here and down there. Let me fix the graph. So this is our base function, x cubed. So that is y equals to x cubed. So usually whenever we graph transformations, transformed graphs, we would usually like to sketch at least 3 graphs that can help us with the stretches and compressions a little. So that would be easier for us to go one by one instead of using a table of values as well. That would help. All right. So first we applied any reflections. So we have the negative sign for the factor of a. So that means we're going to go flip it to the x-axis, over the x-axis. So what that means is that we take the -1, this 1 over here, for example, and it's going to go to -1. Take this 8, move it to -8. Take this -8, move it to 8. And then take this -1, move it to 1. And we also have the origin point, which stays the same. And then we have the first graph. So this is just the first function. So we'll call that graph number 1, where 1 over here represents g of x is equal to -x cubed. All right. So the second graph that we want to graph is the vertical stretch and horizontal stretch. So that means, so by the vertical stretch by a factor of 2, that means we're going to go away from the x-axis. And with the horizontal stretch, we're going to go away from the y-axis. So the second graph we're going to graph, so I'll do this in green instead. So the second graph is when we have g of x is equal to -2. So we're going to use the graph number 1 to graph number 2. And we're going to have the factor 1/3 x to the power of 3. So that way we can use them to graph the other parts as well. So I'm gonna extend the x-axis a little. So we have 3, 4, and we also have -3 and -4. So by the vertical stretch, that means every y coordinate is going to be doubled. And then, so for example, if we take this point over here, that means it's going to be doubled. So from 1, it's going to go all the way to 2. And then with the horizontal stretch, it's going to go away from the y-axis. So it's going to be stretched by a factor of 3, 1/3. So that means it's going to come over here. So that's the point there. And the point on the origin stays the same. But the point over here is going to go vertically stretch, and then horizontally stretch to here. And then we could also graph one other point as well. So we could take this point here. If we vertically stretch it, so we're going to vertically stretch it by a factor of 2. So that means we're going to get about 16 or so. But then we're going to divide it by 1/27, let's say, because if we use our exponent rules a little. So that means we're going to have a point somewhere in between. So let's say what happens, what point number we should use. So for the, let's say we have g at -4. So we're going to have a -2 to, times 1/3 times -4 to the power of 3. Okay, so that means we're going to have -2 times -4/3 to the power of 3. And then that would give us -2 times -64/9, 27, which then would give us 128/27. Now, that is close to about 5-ish around. So I'm just gonna approximate it somewhere. So it's, the second graph would actually look something like this. If I try my best to sketch it like that. Something like that. Doesn't have to be that exact, but at least we could show the transformations a little. And then the last thing that we would do is just add the translations a little. So graph number 3 is when we add all the translations around. So the last graph is just going to be when g of x is -2, 1/3 x minus 1 to the power of 3. So every point in the green, we're going to move it 1 unit to the right. So it's going to come here. This point is going to come over here. This point is going to come over here. So what we'll have is something like this. Something like that. So that's the transform function in purple. So the green graph represents graph number 2, and then the purple graph represents the final transform function. So usually we would have about 3 to 4 graphs representing each transformation using the RST method. And that's why the order would matter, because it would help you with graphing these functions a lot easier. Okay, so we had a look at how to use transformations to graph functions. What about how about describing these transformations? So this example would help you know what is happening to the function, the base function, to actually obtain the transform function g of x. So let's say that we're given the base function f of x is equal to x to the fourth. And the equation of the transform graph is given by g of x, which is 1/4 times 2x minus 4 to the power of 4, and then plus 3. So let's describe the transformations being applied to go from f to g using the RST method. So one thing to note here is that this inside part does not look exactly what we would want. Some people would assume that you're going to go 4 units to the right, but that's not right. Because if we could rewrite this, we would rewrite it like this. Nope. 2 times x minus 2. So we're common factoring out the 2. And then plus 3. So that's something you have to be a little bit careful of. If there's some number that is multiplied with x, you should take that out and make it outside here. So, and make sure you got a common factor out everything else inside. Just so that we have the k unit by itself and do not get mixed up with the horizontal translation. Okay, so let's describe the transformations using RST. So first of all, any reflections? I don't see any reflections because a is greater than 0 and k is greater than 0. So no reflections. So that's 1. Now the second thing here is to describe any stretches and compressions. So we could see that there's a vertical compression. So we have a vertical compression by a factor of 1/4. And similarly, for number 3, we have a horizontal compression by a factor of 1/2. And then the 4 or 5 are just going to be the translations. So we have a horizontal translation two units to the right. And number 5 is the vertical. So we have a vertical translation 3 units up. So that's how we describe the transformations. We usually go left to right based on how the equation is given. So we would start with any vertical compressions, and then we would go to any horizontal compressions or stretches, and then we would go to the horizontal translations, and then we would go to the vertical translations. So that's all for the power functions. Now let's say we want to transform polynomial functions this time. So it's sometimes helpful that, okay, we would like to graph polynomial functions, but also to be able to transform them. So the method is similar as what we did with power functions. The transformation equation is going to be the same thing. So every x that we have that's inside here, that is inside here is going to be replaced by k times x minus d. So that's basically the same idea. So let's have a look at an example where we have f of x to be x cubed minus x squared, be the base function of the polynomial function. And we want to transform it to f to g with the following conditions. So we have a vertically stretched by a factor of 2, horizontally translated 2 units to the left. So only 2 conditions. So we have a to be 2, and we have d to be 2 as well. So how we would rewrite this is that g of x, if we have a times f of k times x minus d and then plus c, Well, we also know that k would be equal to 1 and c is equal to 0 because nothing happens to them. So that means if we put the numbers in, we have 2 times f of x minus 2. So that means we have a factor of 2 on the outside, and then every x inside would just be replaced by x minus 2. So we would have bracket x minus 2 cubed minus x minus 2 squared. Now, here's one thing that we could pay attention to whenever we want to sketch the base function. This function we could factor out a little. So we could say that f of x here, we have x squared, and we would also have x minus 1. So that means we have a 0 of order 2. We have an x-intercept at 0 of order 2. So let's say, so we have x is equal to 0 of order 2. And we also have x is equal to 1, but that one's in order 1. So let's sketch this. So the base function is I'm going to sketch in red. Let's go 1 unit per 4 blocks this time. So we have 1, 2, -1, -2. And then for the y, let's go for, and then for 1, and then -1, -2. So we have something like this to start off with. So we have 0, 0. And then we have the x-intercept at 1. And then we have a point around -2, 0.5. We have something here. And this is what the function would look like. So we have an order 2 function, x-intercept. There's some point down here. Let's say it's about over here. And this is what the base function would look like. All right, so now let's apply the stretches first, which I'll do in blue. So the first graph, we're going to have g of x to be 2 times x cubed minus x squared. So that means every y value now is going to be multiplied by 2 of the base function. So we have the x-intercepts, those won't change. This coordinate will come over here. This coordinate would go somewhere beyond here, which is not really necessary to plot, but let's see what happens. So we have this function now. Looks something like this. So that's graph number 1. And then the last graph here, we're going to apply the transformation. So we are going to sketch g of x. It's going to be 2 times x minus 2 to the power of 3 minus x minus 2 squared. So we're going to translate it 2 units to the left, actually. So that should be a plus instead. So plus, plus. All right. Plus here. Yeah, there we go. So 2 units to the left. So that means we take every point, move it 2 units to the left. Take this point, move it 2 units to the left. Oh, that should be. So 1 would go to -1. This point will come to about over here. And then let's say this point is going to go somewhere over here. So we're going to have something like this now. And that's the idea of transforming polynomial functions. Basically the same thing as what we would do for any power functions or any function that we would use, exponential function, trig function, any function like that. We would use the same transformation rules all the time. So this is the end of the lesson where let's go through what we learned. So the first thing that we had to look at was the transformation function. Where we had to look at the 4 parameters individually. So we had to first look at the vertical stretches and compressions, and then we had to look at what they would look like in application to sketching. And we also had a look at the horizontal stretches and compressions and how it would look like. Horizontal translations, how if d was greater than 0, we would go to the right. When d is less than 0, we would go to the left. And then vertical translations, we had a look at when c is greater than 0, then the function would be going up. And then when d is less than 0, the function is going to be going down. And last one, we had a look at the combination of transformations involving all 4 parameters, a, k, d, and c. And basically, whenever we want to graph transformation functions, we would have to use the RST method. And then we had a look at a couple of examples of how to sketch transformation functions of power functions and how to describe them as well. And the final thing that we had to look at, which was not much, but it's basically how we would be able to transform polynomial functions instead of power functions, which is basically going to be the same thing, but you have to keep in mind about some key points on the polynomial function. For example, you have to pay attention to the x-intercepts and where they're actually going to be. Okay, so that's going to wrap things up for today. If you have any questions, just feel free to let me know. And I'll see you guys in the next lesson.